Okay, so I say, okay, here's our point. It's 0, 9, 30. Here's our normal vector. Again, unit normal is convenient, usually more convenient, it's usually worth the trouble. I'm just going to use the normal vector as we set it. So here's our vector, n, again, equals 0.9i minus 1.1j plus 3.2k. We want to think of the plane perpendicular to this vector. We might represent that plane like so. And the plane has a characteristic that any vector within this plane has to be perpendicular to the normal vector. And the plane has to contain this point. So, and I said every point in the plane because I've been talking about points, but it's every vector in the plane is perpendicular to M. Now, really, vectors don't have a location. A vector just tells you how to move. Remember that, because I have stated this in such a way that I've said the vector's in the plane. Okay? So to state it a little more clearly, just to give you an idea, because sometimes you've got to be real careful about how you state things mathematically. You know what I mean, but it's not well stated, because a vector can't be in a plane. Every vector between 2 points in the plane is perpendicular to the normal vector. It might seem like an unnecessary distinction to you, but it's important to think as precisely as possible at the level of this course, at the level of other courses too. Okay, so, we understand what that means though? The plane's perpendicular to the normal vector. You know, here's a normal vector, here's the plane perpendicular to it. You intuitively know where that is. Okay, if I do the plane like this, well, it's obvious I've got something besides a 90-degree angle there, right? There are all kinds of points in the plane. Okay, well, what we want to do is we want to say, okay, x, y, z, let x, y, z be any point. And let's draw the vector from here to here. That would be, if x, y, z is in the plane, then this is 2 points in the plane, so this vector has to be perpendicular to this, right? So now I can say x, y, z is in the plane if and only if this orange vector is perpendicular to M, right? Now, how would we write the orange vector? What are the components of the orange vector? Can you write them down? It goes from 0, 9, 30 to x, y, z. Okay, now I haven't given you time to completely write it down. I've given you time to think about it. Hopefully you see what it is. It's going to be okay. From here to here, if you want the vector from here to there, you do the vector, or you do the x component or the I component will be the x component of there minus the x component of here. Y component of there minus y component of here. Z component of there minus z component of here. That should be completely clear, at least by the time you finish something about it, okay? Not completely clear now, you want to come back and make it completely clear. Okay? Pretty obvious idea. And I think the problems that you've done, everything's been pretty well done so far. I think you have no trouble with this. So it's in the plane if and only if this vector is perpendicular to M. Okay, well, how do you write the statement that this vector is perpendicular to this vector?
Would it be the cross product? The cross product is the perpendicular, so the x minus 0, that would be the cross product.
Right, you're using the product, you want to use a dot product because if things are perpendicular, it's a dot product at 0, right? Cross product wouldn't be particularly helpful. You do the cross product and then see if it's dot product with other things is what it should be, but you want to do it with the dot product. So, that's a good answer, but you're still sorting these things out, right? So that it's no shame in using the wrong product. But you do want to get used to the idea that your dot product is the go-to test for being perpendicular. Okay? I use IFF for if and only if. Okay? So there it is. Okay. Now we can easily write down that product. Think for a minute how you would write it down if I was going to give you time to write it down. And you know, you would do the component of I times the component of I, the component of J times the component of J, and so forth. So what do you get? You get .9 times x minus 0 minus 1.1 times y minus 9 and then you just do the arithmetic and you see you got 0.9x minus 1.1 y plus 3.2 z. And there are two different ways of writing it. I'm going to write it this way. I'm going to put your constant terms over on the other side. You don't get anything from the 0.9 times 0. 1.1 times 9 is 9.9. And that's minus here, so, well, let's just do it. Okay, we got 9.9 here and minus 96 here, right? And 9.9 minus 96 is negative 86.1. If I did the arithmetic right in my feeble head, that should be 86.1 over here. It'd be negative 86.1 here if you're going to add it to both sides. And there you have it. Okay? So there we have a perfectly wonderful equation of a plane. And notice that our normal vector is sitting right here smiling at us. Right? Right there are the components of our normal vector. Okay? Now let's see what good that might be. Okay, well. Okay. I kind of think I did the arithmetic right, but naturally, trust but verify. Okay. There's your plane. Now let's see what that plane might look like in 3 dimensions. It's not going to look anything like what we would expect from my picture because my picture is kind of oriented wrong. Okay? Doesn't really represent those vectors very well because again, my I component should have been negative 0.9. Okay? Because obviously the I component of this vector should be negative. So what you're going to get is a plane kind of perpendicular something in that direction. So you're going to have kind of this orientation. Let's see what happens. Just to make an analogy with the standard form of an equation of a straight line, or at least one of the standard forms, it's like ax plus by equals c. I'll do this in symbols, but I'll do it in numbers. For example, you got 2x minus 3y equals 12. What's the x-intercept? Just think it, don't say it. Well, the x-intercept occurs if y is 0, right? So, okay, this should be totally obvious. You should have done a lot of this in your Algebra 1, okay, when you're dealing with straight line. And similarly, your y-intercept is 0, negative 4. So your x-intercept is out here, 6, 0. Your y-intercept is 0, negative 4. There's your line. Okay? Just quick reminder, something you might not have had to think about for a while. Okay, well, we're going to do the same thing here. We can find the x, y, and z intercepts. Okay? Once we know what the x, y, and z intercepts are, we can make a sketch that gives us a pretty good picture of where this plane is. Okay? So take a minute, write down the X, Y, and Z intercepts. And you can just write them down, because the numbers don't come out pretty. You just write them down as a ratio, like, 47/3 or whatever, okay? You don't have to do the calculation, just want to see that you're thinking correctly. Won't give you an X-intercept, which is something about this. Oh, yeah, okay, so you got it. Okay. Okay. Yeah, very good. Just want to make sure everybody's engaged here. Not that I've seen any disengagement out there, you all are doing really well. Okay, so the X-intercept occurs when Y and Z are both 0, because any point on the X-axis has 0 for the Y coordinate and 0 for the Z coordinate, right? So, okay? Yeah, so that's approximately 105 maybe, okay? Y-intercept occurs when X and Z are both 0. Of course, if X and Z are both 0, you're left with 1.1y, negative 1.1y equals 86.1. That's about maybe 78. Relay with the calculation. And here, okay. If that was 96, it'd go in 3 times, not 30 times, but that's about 10% less than that. 10% less than 30 is about 27, so I'll say about that, okay? Ballpark, you use your calculator to get it more accurate. So we have the X coordinate, which is maybe the X-intercept, sorry. The Y-intercept, which is around 78, a little less than the X-intercept, get a little careless with the perspective and stuff, but okay. 0, 78, 0. And then the Z component, which is quite a bit smaller, about 27. These are all approximate. Implicitly, this is approximate as well. So now, if we want to see this plane, we just say, okay, well, let's see, we do a triangle here. And now we see how the plane lies. Okay? Not real steep. And oriented out this way into the first octave. Okay? Oh, I screwed up here because one of these is negative. Right? Because now, I looked at it intuitively and said, nah, normal vector's not into the first octave. It looks like it's out into the third octave. Okay? so now I'm gonna have to fix my pretty picture. I'm gonna ask you to do it, okay? You never know whether I did that intentionally or not. I want you to do it, okay? Show me where it ought to be. And yes, I did it unintentionally, but we'll make something good out of it.